In this short video, we're going to learn all about how to solve a multi-plant monopoly question. Perfect Comfort is a multi-plant monopolist producing cozy cat beds. They face an inverse market demand curve of 20 minus 0.5 Q and a marginal revenue curve of 20 minus Q, where Q is the number of cat beds produced. They operate out of more than one plant, and plant 1 has a marginal cost function of 2 plus 0.5 Q1, while plant 2 has a marginal cost function of Q2. Additionally, we're told that total output in the market is the sum of Q1 and Q2, where Q1 is the number of cat beds produced in plant 1 and Q2 is the number of cat beds produced in plant 2. We are going to do two things in this question. We're going to determine Perfect Comfort's profit maximizing total output as well as the price they're going to charge. And then we're going to determine how they should allocate their total production between the two plants. So we're going to solve for Q1 and Q2, as well as the total output and the optimal price. What do we need to know in order to answer this question? It actually turns out that all we need is each plant's marginal cost curve, as well as the inverse demand curve. And not on the slide, but we need that detail that Q is the sum of Q1 and Q2. How are we going to solve this question? Well, to answer part 1, we're going to find the total marginal cost curve by horizontal summation, and then we're going to set that total marginal cost curve equal to marginal revenue to find Q. Once we know Q, we substitute it into the inverse demand curve to find price. So this is a standard monopoly question with a twist, and the twist is that the first thing we need to do is find this total or aggregate marginal cost curve. How do we solve question 2, the optimal allocation? Well, we need to apply the optimality rule here. The optimality condition says that we need the marginal cost in plant 1 from producing Q1 units to equal the marginal cost in plant 2 from producing Q2 units to also equal the total marginal cost of producing the total output. So to solve this, what we'll do is we'll find the marginal cost from the optimal output, and then we'll make sure that the plant 1 and plant 2 also have that marginal cost. It turns out to be not as hard as it sounds, I promise. So let's solve this question. Here's what we know. We have an inverse demand curve, associated marginal revenue curve, the marginal cost from our two plants, and we have information about the fact that the total output is the sum of production in plant 1 and production in plant 2. The first thing we're going to find is the profit maximizing quantity and price. So we start by making a little plan. We know we need to find the total marginal cost curve, set that equal to marginal revenue to find Q, and then substitute that Q into the inverse demand curve to find price. So the first thing we're going to do is find that total marginal cost curve. How do we do that? It's a horizontal summation process. That means fix price, add Q. And if we're going to fix price and add Q, we need to invert both the marginal cost curves first. So the process will go like this: invert, add, reinvert. It's algebraically annoying, but not difficult. So invert means take a look at marginal cost 1 and solve it for Q1. So I'm just going to rewrite it. Marginal cost 1 is equal to 2 plus 0.5 Q1. I'm trying to solve for Q1, so I have marginal cost 1 minus 2 is equal to 0.5 Q1. And then I multiply both sides of the equation by 2. And when I do that, I get that Q1 is equal to 2 marginal cost 1 minus 4. So that was annoying. Inverting the marginal cost 2 curve is a lot easier. In fact, there's no work involved at all. Solving this for Q2 tells us that Q2 is equal to marginal cost 2. So we've inverted them. With our two inverse marginal cost curves, we can now horizontally sum them. What does horizontal summation mean? Really, we're relying on this fact that the total output in the market is equal to Q1 plus Q2. And from our two inverse curves, we know how we can write Q1 and Q2 as a function of marginal cost. So at this point, what I'm going to do is I'm going to add and I'm going to drop the subscripts on the marginal costs. So I have Q is equal to 2 marginal cost minus 4 plus marginal cost. Why can I drop these subscripts? because I'm assuming that the marginal cost is equal across the two plants as I add. I'm fixing marginal cost and I'm adding Q1 plus Q2. So this is the horizontal summation process where we're adding what's along the horizontal axis. So doing a little simplification, I get Q is equal to 3 marginal cost minus 4, and I can call this equation 3. We are one step away from finding that total marginal cost curve. We inverted, we added, and now we need to reinvert. So we're going to take equation 3, which is the horizontal sum of the two inverse marginal cost curves, and we're going to invert it to find the total marginal cost. So invert here means solve for marginal cost. So I'm going to focus on this function right here. I'm going to add 4 to both sides. So I have Q plus 4 is equal to 3 marginal cost. And then I'll divide both sides by 3. And I'll rewrite this in the following way. The total marginal cost is equal to Q over 3 plus 4 thirds. And we'll call that equation 4. So it may not seem like it, but we've actually done all of the hard work, and all that's left is pretty straightforward. We found that total marginal cost curve. We're going to set it equal to marginal revenue and solve for Q. So we have Q over 3 plus 4 thirds is equal to the marginal revenue of 20 minus Q. Now I'm very annoyed by the fractions here, so the first thing I'm going to do is multiply both sides of my equation by 3. When I do that, I get Q plus 4 is equal to 60 minus 3Q. Now I'm feeling less annoyed, and I can solve for Q by collecting all my Q terms on the left-hand side of the equation. I have 4Q is equal to 60 minus 4, which is 56. And when I divide both sides of this equation by 4, I get that Q star, the optimal slash profit maximizing quantity, is equal to 14 units. The final step to finding the profit maximizing quantity and price is to take this Q equals 14 and substitute it into the inverse demand curve. So we have P is equal to 20 minus 0.5 times 14. A half of 14 is 7. 20 minus 7 is equal to $13. So we've done it. We solved for the profit maximizing total quantity, which is 14, as well as the price. But we still don't know how we should divide this total quantity between plants 1 and plants 2. Okay, so what are we going to do next? We need to find the optimal division of output between the two plants. In order to do this, we're going to apply that optimality condition, which says that the marginal costs across the two plants have to equal each other as well as the total marginal cost. So I'm going to write a few useful equations down. These are things we've already solved for. We have our inverse marginal cost curve 1. We have inverse marginal cost 2. We have the total marginal cost as well as the total output that should be produced by this firm. What are we going to do with this? Well, the first thing we need to do is determine the firm's marginal cost when Q equals 14. Why? Because once we know the total marginal cost, we can figure out how to divide the output between the two plants by making sure that marginal cost 1 and marginal cost 2 also equal this total marginal cost. So we're just going to evaluate MCT at Q equals 14. So marginal cost is equal to 14 divided by 3 plus 4 divided by 3. Don't get confused and think this is going to be a fraction. Instead, notice that they have a common denominator. So we can write this as 18 over 3, which is of course equal to 6. So the marginal cost for this firm of producing 14 units is $6. And we now need to make sure that plant 1 and plant 2 also have a marginal cost of $6. This process is going to turn out to be very simple. We just need to determine the Q1 and Q2 that make marginal cost 1 equal to 6 and marginal cost 2 equal to 6. And we're lucky because we've done a lot of work already, and we already know how output depends on marginal cost 1 and how output depends on marginal cost 2. So what we do is we take 6, the marginal cost, and we replace it in equations 1 and 2, and that allows us to solve for Q1 and Q2. So Q1 is equal to 2 times the marginal cost, which has to be 6 under the optimality condition, minus 4. Well, 12 minus 4 is 8. And Q2 equals marginal cost 2, but marginal cost 2 has to equal 6 if we're optimal, because the marginal costs have to be equal across plants and equal to the total. So we just said Q2 equal to marginal cost 2, which is 6. So we figured out that the firm should charge a price of $13 and produce 14 units, and those 14 units should be divided amongst the plants in the following way. 8 units are produced in plant 1 and 6 units are produced in plant 2.